Big questions still remain about 3I Atlas. Now, a lawmaker is pressing NASA for new images of the space phenomenon, and could it also have a traveling companion?
Astronomers just spotted something impossible. A strange object speeding through our solar system, leaking a metallic gas no one has ever seen in space before.
But this rock in question is headed our way. It's called 3I Atlas, and it is set to get as close as 167 million miles away from Earth by December 19th.
The Webb telescope's readings show it's coated with a reflective alloy that seems to repair itself as if it's alive, or maybe designed.
Now, as of this morning, some observers noticed that it has a set of jets around it, more than 7.
Scientists say it could rewrite what we know about comets, chemistry, or even intelligence beyond Earth. What exactly is 3I/ATLAS hiding? Join us. The interstellar visitor that breaks physics. The Webb Space Telescope recently detected strange emissions pouring out of an object known as 3I/Atlas, and what it found has stunned astronomers across the world. Instead of behaving like a normal comet or asteroid, this interstellar traveler is releasing an alloy that shouldn't exist naturally in space. The same kind of compound that humans only ever see in factories and aerospace facilities. Are we potentially looking at something that was built, not born? 3I/Atlas first entered the conversation quietly, its name standing for Third Interstellar Object Tracked by the Atlas Survey. Astronomers recognized early on that it wasn't local, as its orbit wasn't bound to the Sun, meaning it had come from outside our solar system. Its speed and trajectory confirmed it was on a hyperbolic path, swinging through from interstellar space and heading back out again, never to return. Objects like this are incredibly rare. Only 2 others have ever been confirmed before it: the mysterious Oumuamua in 2017 and Comet Borisov in 2019. But unlike those 2, 3I/ATLAS has broken nearly every rule scientists thought they understood about what an interstellar object should look like and how it should behave. When telescopes began analyzing its emissions, the first surprise was chemical. Spectroscopy, the process of studying the light emitted or reflected by an object, revealed that 3I/ATLAS was releasing significant amounts of nickel into space. That in itself was strange, but what truly alarmed scientists was what wasn't there: iron. In every natural comet ever studied, nickel and iron always appear together. They're formed side by side in supernova explosions and locked together inside primitive rock and ice. They're chemical siblings. You can't separate them under ordinary natural conditions. Yet 3I/Atlas was breaking that cosmic rule. Nickel was gushing out at a steady rate of about 4 grams per second, and iron was completely absent. On Earth, the only place that produces such a clean separation between nickel and iron is in controlled industrial processes, and one compound in particular stood out: nickel tetracarbonyl. It's a highly specific engineered molecule used in metallurgy, especially in aerospace applications. When nickel reacts with carbon monoxide under pressure, it forms nickel tetracarbonyl gas, a toxic, volatile compound that can be decomposed to deposit pure nickel onto metal surfaces. Humans use it to harden aircraft parts and improve the strength and reflectivity of alloys. There's no known natural process that can make or sustain this compound in open space. Yet the plume detected from 3I/ATLAS appeared chemically consistent with exactly that. One of the first scientists to acknowledge how strange it was, Harvard astrophysicist Avi Loeb, pointed out that this kind of nickel-carbon chemistry has never been observed in any natural comet. He noted that the behavior of 3I/ATLAS, the way it emitted nickel without iron, and the steady, concentrated jet that accompanied it, looked eerily similar to industrial metal processing. The mystery deepened further when the direction of the emissions was examined. In every ordinary comet, sunlight heats the icy surface, causing gases to escape and form a glowing tail that always points away from the sun. Solar radiation and wind push that material outward. But 3I/Atlas refused to play by those rules. Observations from Hubble, and later confirmed by the Keck telescope, showed that instead of shedding material away from the sun, its jet was pointed toward it, firing directly into the heat. And to make things stranger, the jet didn't just stay steady, it pulsed. The emission strength rose and fell at near regular intervals, suggesting that 3Y/Atlas might be rotating while venting material in a timed rhythm. Or at least altered by some intelligent process. To be clear, no one is claiming this is an alien spacecraft. Scientists are careful with their words, but they're equally clear that something about this object defies the known rules of comet behavior. The Webb telescope's latest infrared readings suggest that the emissions are continuing, and that the brightness of 3Y/ATLAS remains unusually high for its distance from the Sun. This means the object is maintaining or even enhancing its structure over time. How telescopes caught the impossible signal? How could a telescope parked nearly 1 million miles from Earth detect an alloy leaking from a tiny, fast-moving object hurtling through space? And how do scientists even know that the signature really belongs to nickel and not to something else entirely? The answer lies in one of astronomy's most powerful tools: spectroscopy. Every element and molecule in the universe absorbs and emits light in a unique pattern, like a barcode. When white light passes through a gas, or when an object glows, certain colors disappear or appear at very specific points in the spectrum. These tiny shifts in color tell scientists exactly what materials are present, even if the object is too far away to ever reach physically. For 3I/ATLAS, the key data came from its visible and infrared spectra, the light scattered from its glowing jet and sunlit surface. By splitting that light into thousands of narrow bands, the Webb telescope and its ground-based partners could identify which wavelengths matched known substances. In this case, the peaks lined up perfectly with nickel vapor, particularly the signature seen when nickel atoms are excited to high energy levels. Scientists immediately sought cross-verification, meaning they compared Webb's data with readings from other telescopes to ensure nothing had gone wrong in processing. The Keck Observatory in Hawaii, equipped with one of the world's most precise optical spectrometers, confirmed the same pattern. Later, archived data from the Hubble Space Telescope, taken weeks earlier, revealed that the same spectral line had been present even before the Webb reading, though faintly. Still, astrophysicists are cautious by training. In spectroscopic analysis, noise can creep in through many channels, cosmic rays hitting the detector, subtle electronic interference, or temperature fluctuations that alter how sensors read incoming photons. Instruments must be meticulously calibrated. Even then, atmospheric interference from Earth can distort light for ground-based telescopes. To eliminate these distortions, researchers often combine space-based and Earth-based observations. Webb, operating beyond Earth's atmosphere, captures the pure signal, while ground telescopes provide repeated measurements from different vantage points. When the same pattern appears in both, scientists gain confidence that the signal is real. In the case of 3I/Atlas, the nickel lines were seen at multiple wavelengths, from multiple platforms, at multiple times. To appreciate just how unusual this is, it helps to compare 3I/ATLAS with the two previous interstellar visitors. The first, Oumuamua, detected in late 2017, was a slender, elongated body that defied easy classification. It lacked a visible tail, but accelerated slightly as if pushed by something more than gravity, perhaps gas outgassing, perhaps something else. The second, Borisov, discovered in 2019, behaved much more like a traditional comet, shedding dust and ice as it swung past the Sun. Both of these objects, however, were chemically ordinary. Their spectra showed simple combinations of hydrogen, oxygen, carbon, and nitrogen, the building blocks of typical comets formed in the outer reaches of solar systems. 3. I/Atlas breaks that pattern completely. It is larger, brighter, and chemically alien in a literal sense. The ratios of nickel to carbon to hydrogen simply don't match anything seen before. Its emissions are dominated by metals rather than volatiles, meaning that its active surface isn't just ice turning to vapor, it's metal turning to gas. Even more curious is how steady its emissions are. Ordinary comets sputter, with gas output fluctuating chaotically as they rotate and heat unevenly. 3I/Atlas's output is almost rhythmic, implying some kind of internal regularity or self-regulating process. Another piece of the puzzle comes from its motion. The orbital path of an object like this can be predicted precisely using Newton's laws of gravity. But when scientists plotted 3Y/ATLAS's trajectory, they found tiny deviations, what they call non-gravitational accelerations. These are minute changes in velocity that can't be explained by gravity alone. Usually, such deviations are caused by jets of gas escaping from one side of a comet, giving it a small push. But the direction and strength of the push from 3Y/ATLAS doesn't support this theory. The movement was consistent, as though a force were being applied deliberately in just the right direction to maintain stability. That kind of precision is what made astronomers uneasy. The numbers didn't suggest a powerful engine or anything of that scale, but they did imply that the object's emissions were having a measurable effect on its motion, one that was not chaotic, but predictable. In astrophysics, that kind of regularity hints at structure. It could mean the object has internal chambers directing the flow of material or layers that heat and vent sequentially. Either explanation challenges current models of comet formation. There's also the question of energy balance. The energy output required to vaporize nickel at the observed rate is enormous. For a natural comet, sunlight alone would be insufficient to sustain that level of heating unless the object contains some unknown catalyst or reactive compound. That suggests one of two possibilities. Either 3I/Atlas harbors materials that interact in ways we haven't encountered before, or something about its surface allows it to convert solar energy far more efficiently than expected. Researchers have run simulations to test whether ordinary physical processes, say buried carbon compounds reacting with nickel sulfides, could reproduce the same spectra. So far, none have succeeded. The results simply don't fit any standard chemical or thermal model. That's why so many observatories, including the European Southern Observatory and NASA's Jet Propulsion Laboratory, continue to collect data every few weeks as the object fades into the outer solar system. Still, the scientific community remains divided, balancing skepticism with fascination. Could there be an undiscovered mineral phase that explains everything? Possibly. Could we be misinterpreting the nickel line altogether? That seems unlikely after so many independent confirmations. Even when all uncertainties are accounted for, from instrumental noise to data calibration to modeling assumptions, the conclusion doesn't change. The nickel signal remains consistent across instruments, times, and wavelengths. It is real, stable, and unexplained. What this metal could really mean, if the data from 3I/ATLAS is correct, and by now almost every major observatory agrees that it is, then scientists are faced with two extraordinary possibilities. Either this object represents a kind of natural chemistry never before seen in the universe, or it's behaving in a way that suggests engineering, not accident. Which of those is more likely? And more importantly, how could we ever tell the difference? If the nickel emissions from 3I/ATLAS are natural, that would signal the discovery of a completely new type of cosmic chemistry. On Earth and in our solar system, metallic compounds like nickel carbonyl can't survive long without containment or protection because they are unstable when exposed to ultraviolet light or vacuum conditions. But if the object somehow contains layers of carbon monoxide trapped beneath its surface, perhaps compressed under high pressure during its formation in a dense molecular cloud, it could be generating the gas internally. When sunlight hits, the heat might release bursts of nickel and carbon monoxide together, which then react to form the same compound humans make in industrial furnaces. That would mean 3Y/ATLAS is effectively performing a natural version of metal vapor deposition, a process that, until now, has been exclusive to factories and laboratories. To confirm this, scientists are looking for clues in how the emissions change over time. If the nickel output fluctuates with the object's rotation or distance from the sun, it could suggest a thermal cycle, a heating and cooling pattern that drives natural chemical reactions. In that scenario, the bright metallic coating seen on its surface could be a kind of protective crust, formed when nickel vapor cools and condenses back onto the body. This would be unlike anything seen in the solar system, showing that even simple metals can play an active role in regulating a comet's structure. But what if this isn't natural chemistry at all? What if the behavior of 3I/ATLAS, the directionality of its jet, the precision of its pulsing, and the steady plating of its surface points to something more controlled? If that's the case, scientists are beginning to consider whether they might be observing a self-repairing probe, the kind of autonomous technology that theoretical astrophysicists have speculated about for decades. Imagine a spacecraft made of intelligent material, capable of sustaining itself for thousands of years between the stars. Such a probe could use metal vapor plating to heal micro-damage, strengthening its surface against radiation and heat. It could vent metallic gases not as waste, but as part of a thermal control loop, releasing material toward the sun to stabilize temperature and spin, then reabsorbing it to maintain balance. Of course, the first objection to that idea is obvious. How could any engineered molecule or mechanism survive the vacuum of interstellar space for millions of years? Nickel carbonyl, the compound at the heart of the mystery, is extremely unstable by human standards. It breaks apart in sunlight within minutes, which makes its sustained presence around 3Y/ATLAS difficult to explain. The only way such a compound could persist would be if it were being continuously regenerated, either through ongoing chemical reactions or through an active process that replaces what decays. To explore these questions, scientists are turning to more specialized tools. The Webb telescope will continue gathering high-resolution spectroscopy, which can detect even smaller variations in the emitted wavelengths. Meanwhile, the SETI Institute has already scheduled radio scans to search for any artificial electromagnetic signals near 3Y/ATLAS. These are not meant to listen for aliens in the traditional sense, but to detect any narrow-band emissions, precise, repeating radio patterns that nature rarely produces. Plus, NASA, the European Space Agency, and several university observatories are sharing open access data under what's called an open data policy, meaning that the raw readings from Webb, Keck, and other telescopes are made publicly available for independent verification. This transparency allows any researcher to test alternative explanations and helps prevent the kind of sensational claims that often follow discoveries like this. The goal is to ensure that the evidence speaks for itself, without bias or premature conclusions. And skepticism is not just encouraged, it's essential. The scientific community remembers how quickly speculation spiraled after the discovery of Oumuamua, when early reports of its unusual shape led to years of debate about whether it might be artificial. Many researchers now emphasize that unusual data doesn't automatically mean intelligent design. Extraordinary claims demand extraordinary evidence, and right now, all that exists is a strange chemical pattern and an even stranger jet. Before jumping to conclusions, every alternative, from exotic magnetochemistry to undiscovered mineral structures, has to be ruled out. But skepticism also has limits. At some point, when every known natural mechanism fails to account for the data, the question must shift. If this object is obeying rules that don't exist in current models, then those rules need to be rewritten. If its behavior implies engineering, then that possibility deserves the same serious consideration as any natural explanation. For now, researchers are proceeding cautiously, aware that their work could either expand the boundaries of chemistry or redefine what it means to observe intelligence beyond Earth. There's also a deeper, more philosophical challenge hidden in this discovery. Whether 3I/Atlas turns out to be a natural phenomenon or an artifact, it's forcing scientists to rethink how they identify life or technology. On a cosmic scale, the line between biology, chemistry, and machinery may not be as sharp as humans assume. An interstellar object capable of self-regulation and metallic renewal might not fit any category we have. Not a spacecraft, not a rock, but something in between. In the months ahead, more data will come in, and the models will improve. But no matter what they show, one conclusion is already clear. Something extraordinary passed through our solar system, something that challenges our understanding of how matter and intelligence might coexist in the universe. Either nature is far more inventive than we've ever imagined, or we just encountered the remnants of someone else's invention. Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.